In this video series, we're looking at Unity joints. Now today we're going to be looking at the spring joint, and in the previous video we went through the fixed joint, so make sure to check that out. But today we're doing the spring joint. So going into this project, we see we have the cube, it has the fixed joint, and there's no connected body. However, cube 2 has a rigid body, so if we press play, this should stay connected up here and the other one should fall. Alright, so I'm going to add a spring joint. Let me go ahead and add it to this rigid body. So I'm going to type joint, and then here's a spring joint. Alright, let me press play. And that's what it does. It acts like a spring. So let's look at the documentation. And the spring joint joins two rigid bodies together, but allows the distance between them to change as though they were connected by a spring. Alright, let's go through the properties. Connected body. This is the rigid body that the object with the spring joint is connected to. If no object is assigned, the spring joint will be connected to a fixed point in space. So right now I have no connected body, so it's connected to a fixed point in space. That point is actually this anchor. And you can see it right here. It's this brown square. If I move it, you'll see that it moves. Now that's the point that it's connected to the spring. So if I were to move it over here and press play, then it's connected to this point. Now there's no rigid body, so it's not connected to another rigid body. It's connected to that point wherever that brown dot is. It's connected to that point in the world space. Now by default it came at 0.5 and it's 0 on the x-axis, so right there above the cube, and we'll see that that's the point where the spring is connected to. Now we can add a rigid body. I'm going to add the cube, so now it's connected to the cube. So if I press play, we're going to see the same behavior because this cube actually has a fixed joint, so it's stuck up here, and it's not but they're connected with a spring, but this one's not going to move. It's stuck in place because of that fixed joint. Now going down the list of parameters or properties, we've already looked at the anchor. This is the point in the object's local space at which the joint is attached. So we already seen how that works. But now we're going to have to look at the connected anchor, because now that we have a connected rigid body, there's a place on that object where the spring is also connected to. And there's an option to auto-configure that place. So if you want Unity to calculate the position of the connected anchor point automatically, it can do that, or you can configure it manually. So let's see how that works. Here's the connected anchor, and it's configured manually. So if I press play, we're going to see that it's the connected anchor is actually in the same exact spot as it is. So both anchors are right there. 0.5. This is the anchor for this object, and I'm going to move it. We can see it move, and then because it's auto configuring, it's setting this one, it looks like, to the same exact position. So if I uncheck this, we're going to get control over both of those. So now I can move this one, but I can also move this one. So the anchor is the one, the point where the spring is connected to on this object. So I want that one to be right there at the top. That's the 0.5 position. But I basically want this one to be at a negative 0.5 so that it's down here on the bottom of the cube. So I'm going to say negative 0.5. Alright, now I see the connected anchor is here. No, let me fix that. The anchor is here, and the connected anchor is here. So the spring's going to go between these 2 points. I'm going to press play, and let's see what we got. We've got the spring connected between those 2 points. Now we can configure where that point is, of course. We can move the connected anchor over to this edge like we had done before. And then it's going to be, the spring's going to be more connected over there. It could be even way over in space, in the middle of nowhere over there. And then we're just going to get some funny behavior with the spring because it's acting more like it's connected to a invisible world space place right here. So it seems like the most realistic is going to be if that connected anchor is on the face of the object it's connected to. In this case, we're going to go to 0, -0.5. And I like it to be right there in the middle. Now the next property is the spring. This is the strength of the spring. So right now it's set at a 10, and we get a nice bounce. Not a very strong spring, kind of weak. All right, let's change it to 50 and see what we get. Much stronger spring. And what you're going to see is this really changes the distance between the two objects depending on the object's mass. Obviously, with more mass, it's going to pull on the spring harder because it has more weight. But if I adjust this in real time, we'll see that increasing it up to a 100 will basically make it so the objects are really close together. And lower all the way down to 10 is going to make it so that the objects are quite far apart. And actually it looks like with a spring of 10 and having these two objects with a mass of 1, that the spring seems to stretch about 1 meter, 1 unit. So I just made a new 1 unit cube, and we'll see the distance that spring makes is about 1 unit. So just a random fact there, if you have two objects with a mass of 1 and your spring is has these values, the default values basically, then the spring will stretch out 1 cube. Now if this got heavier, that spring is gonna stretch even more. So really this spring represents the strength of the spring, and the spring acts like a piece of elastic that tries to pull the two anchor points together to the exact same position. So we have this anchor point and we have that, and the string is going to try to move these 2 points into the exact same position. The strength of the pull is proportional to the current distance between the points, with the force per unit of distance set by the spring property. And so that's what the spring value is for. I'm going to put it back on a 10 so that it makes a distance between them of about 1 unit. And the next one to look at is the damper, and this is the amount that the spring is reduced when active. And that's a little hard to understand, so let's read down here. To prevent the spring from oscillating endlessly, you can set a damper value. And by oscillate, we mean to move or swing back and forth. So what it's saying is to prevent the spring from swinging back and forth endlessly, you can set a damper value that reduces the spring force in proportion to the relative speed between the two objects. And a good example of that is going to be if we change these. Let's move it like this, and then when we start, it's going to have a really big swing on it back and forth, or even worse, and give it a real nice swing there back and forth. Let's see how the dampening value changes that. We have the damper here, and it's set to 0.2. So I'm going to put it all the way up to 1. That's not a very big change, actually. It's going to be just about the same. And it's going to take quite a while for this to get back to the middle point to where it's not swinging back and forth anymore. And to reduce that time, we would increase the damper. So if we set this to 50, there's going to be less swinging back and forth, less rotation, less extreme rotations when it's swinging too. So the spring value affects the strength of the force applied to the proportional to how far the object is away from its intended spot. So that's basically how strong the spring is. But the damper value affects the momentum of the spring, which is basically its tendency to overshoot and oscillate back and forth. Higher value for the damper will make the spring come to rest much faster, whereas a lower damper value will allow it to swing back and forth for a longer time before eventually coming to rest. So it just, I guess it depends. I think it's a pretty clear difference you can see there between having the dampening at a default of 0.2, where you play it and it makes some really extreme rotations right here, there, and there. It's making some pretty extreme rotations, especially that first one and second one. And if we increase that damper up, let's put that on 100, we'll see that it doesn't have those crazy rotations. It looks more natural, I guess, there. Now moving on, we have the minimum distance, which lower limit of the distance range over which the spring will not apply any force. All right. This is a little hard to visualize, and I think the best way to do it is going to be to put both of these cubes onto the ground. So I'm going to put a y of 0.5 and a y of 0.5 here. And so we got cube 1 and cube 2. I want them to be connected between the spring right here. So let me go change this. It's going to be on the x negative 0.5, 0, and there it is. And then the connected point is going to be 0.5, 0. Because again, this is the object's local space. Alright, so now the spring's connected between them there. And we know by default this is going to go 1 unit before it before the string starts pulling. So if I press play, first of all, let me get rid of the fixed joint on this, so both the objects can move freely. And I'm going to select the second cube. And first of all, let's line these up on a grid nicely, since the grid deals in 1 unit blocks as well. That's better. Let me press play. And what's going to happen is the spring is acting like it's a connected joint. I got both of these objects selected, so let me just select one, and here we go. Now I can move this box, and the spring really isn't going to do anything until it gets 1 unit apart. So right about now it should start pulling, and we can see the spring has pulled the objects apart. Alright, let's visualize that with a 3D object. We could use a capsule, and let's do a 0.1 and a 0.5. That's 1 unit large, and we'll rotate it 90 degrees. So this represents the spring. It should be about 1 unit. And it's right there in the middle, and I'm going to turn off the collider so it doesn't get in the way. And so if I pull this box, when we get to the edge of 1 meter, at the edge of this white graphical indicator, we're going to pull. We'll see that we pull. So this is representing the spring. Now, the minimum distance. This is the lower limit at which the spring will not apply any force. And we can look at this here to where it says the minimum distance and max distance value allow you to set a distance range over which the spring will not apply any force. You can use this, for example, to allow objects a small amount of independent movement, but then pull them together when the distance between them gets too great. It's still a little confusing. The minimum and maximum distances act as hard limits to the spring to prevent the objects getting too close together or too far apart. Still a little bit confusing. Let's look at exactly what's going on here. Without any minimum distance setup, we know that the spring's going to pull at 1 unit. So let's set a minimum distance of 1. And I'm going to press play. Now what's happening is there's a minimum distance from the starting point, which the starting point is this. So let me just swap sides of these cubes, which means I'm going to have to change the anchor position, but that's easy because it's just a negative and a positive swap. All right, because I want this to be the beginning, the spring joints at the beginning here. So now it has a minimum distance of 1. Now what that means is there's a minimum distance of 1 unit before the spring exists, essentially. So if I press play right now, what should happen is the spring doesn't exist from here to here, or even all the way to here. But once that minimum distance of 1 has been passed, then the spring exists here. So once I get to this line, it should pull the objects together. Okay. Now when you get the max distance, it starts getting a little confusing. So first of all, I'm going to put in a max distance of 1, and let's try this again and see what happens. And what is going to happen is we've set the minimum distance to 1, but the maximum distance is also set to 1. So now the maximum distance also starts from the beginning. It doesn't start from where the minimum distance ends. So if I count this out and we say it has a minimum distance of 1, we can say 1, and then let's go to the maximum distance, 1. Okay, this is the location of the minimum and the maximum distance. So that means if I pull, that means the spring's going to exist here. So if we pull that cube in this direction, it's going to pull right there. But because the minimum and the maximum distance are at the same location, we will have the same behavior that we did when minimum distance was set to 1 and maximum distance was set to 0. Nothing will happen this way, and when we pull here, we'll just have the cube pull there. All right, so let's take it out to 2. So we got the max distance at 2, the minimum distance at 1, and what that means now is there's a minimum distance of 1, then the spring exists, and then there is a maximum distance of 1, and then the object, and then the anchor point is essentially where it's going. So I should be able to start it right here, and they're not going to pull together. I should be able to go all the way down here, all the way this way. But when we get to here, it should pull because, well, let's see, we have a minimum distance of 1. So then the spring starts, and then we have a maximum distance of 2. So 1, 2. And that means that when we get to this point, that's going to start pulling. So our minimum distance is 1. However, we now have a maximum distance of 2. So we have to go 1, 2. And that is where the spring would start, at the max distance in this case. So the spring would actually exist here at the max distance. So let's hit play. And we'll see that we should be able to move this cube all the way up to here. But when it gets to its max distance, it's going to start pulling together. All right, so let's now take it up one more just to make sure that we get the concept right. In this case, the minimum distance is 1. So this is the minimum it can go. However, it has a max, which means it goes to 3, which is 1, 2, 3. And then we know the spring, so this is where it starts. The spring starts, or essentially the anchor point starts here. And then we know the anchor point ends here because here it is. So the spring should essentially exist about here. And if I hit play, we should see that I can move it all the way up here. And when I get to this point, the spring pulls. All right, so we can see kind of how this works a little bit more if I move the max distance up to 6. And then we're going to bring the minimum distance up to match. So we got 1, 2, 3, 4, 5, 6. So the spring should be in that position. And if I select the cube and move it over, when it gets to that 6 units, it should start pulling. Oops, I think I miscounted one. So we got a minimum max distance of 6. So that's 1, 2, 3, 4, 5, 6. Yep. And so the spring would start there at 6, and it would be 1. Now when we pull the box over here, we should get the spring pulling right there. Okay, good. All right, now we can set the minimum distance to something else. We could move it up to, say, 4, or let's go all the way up to 5 so that we just have a 1 unit gap. So now we say 1, 2, 3, 4, 5. So the minimum distance is here and the max is here. We're really going to have the same behavior that we did before, except now there's a max distance, a minimum distance of 5 in between these, and there's only 4 units here. So when we start, it should push those away from each other because they have to be a minimum of 5 apart from each other. So we're going to see a little bit different behavior here where it should essentially pull at this point right out here. And then when we push it in, it should 1, 2, 3, 4, 5. It should not allow it to get too much closer than that minimum distance. All right, moving on. The tolerance also has to deal with this because if you look at the tolerance changes air tolerance. This allows the spring to have different rest length. And you can see that the spring joint tolerance is the maximum allowed air between the current spring length and the length defined by minimum and maximum distance. If the tolerance is set very high, the solver might not run and the spring would effectively not exist. If the tolerance is set close to 0, very short spring lengths are possible, but at the increased cost of running the solver more often. So the best way to look at this is to say that essentially it's the maximum allowed air between minimum distance and max distance. So a higher value might perform better, but a lower value is more accurate, and it's default to 0.025. In the case of this, I wouldn't care if it was 0.1 incorrect. It doesn't need to be that accurate, but again, the default value is probably fine there. And if we had a tolerance of 1, what would happen is, let's reset this down to 0. And at 0, basically where we're at is the spring is going from here right to there. So at a tolerance of 0, we should get the spring pulling when we, or with minimum and max distance set to 0, we should just have the spring pull right where these anchor points exist. All right. So if we go and we set a tolerance of 1, then it can have an error of up to 1. And that should mean that it probably isn't going to pull the spring until I get all the way up to a whole unit away, 1 away. Because it's right now it has a tolerance of 1, so it's going to go all the way here before it starts pulling. So that's what the tolerance is. A lower value is going to be more accurate and cost more to calculate, I guess. And a higher value will make your physics a lot less accurate. So I guess I'll stay with the default value of 0.025. And then there's brake force. And we've already looked at brake force in the previous video in the fixed joint, but brake force is just a force that's needed to break the joint between the two. So right now it's set to infinity, and if I were to set that to 1 and press play, and then I go pull on this box, it's probably going to hit a in fact, it's already broken. There is no joint. So let's try that again. Let's put a brake force of 10. All right, it's not broken yet. So if I go to the scene view and I move this, we'll see it just disappeared because the joint broke. Now if we bring that up to 100, we should get some kind of a pull on the box before that joint breaks. There we go. But it's still possible to break. Well, I didn't get it to break, but it will break if it has a force of 100. We could try it with like 20 and then see if we can get it to break by pulling like this. There it goes. It just broke. All right, so that's what the brake force is. The brake torque is the same, except it's the rotational brake. So if I were to set the force back to infinity, it'll never break with force. However, I set the torque to 10, it will never break by moving it like this. But if it gets a rotation, if it gets a torque force, then it'll break that joint. So let me go ahead and press E on the rotator, and I'm going to rotate it, and we should get it to break. But the brake torque is the rotational force, and if the joint's going to break with the rotational force. So then we got the enable collision, and enable collision is just if these objects are going to collide while the joint exists. So right now, if these can go right through each other, but if you put on enable collision, they're going to run into each other. So that only matters when the joint exists, because if you break that joint, which it just broke, then they go back to their box collide or rigid body collisions, and they're going to collide with each other. So a good example of that is right now there's not collision enabled, and if the objects run into each other, no big deal, nothing will happen. But if that joint breaks, now there's no joint, so they're going to collide with each other because they both have colliders and rigid bodies. So this Boolean value is just if they're going to collide with each other while the joint is active. That's it. So while the joint's active, do you want the objects bumping into each other or not? Okay, and we got enable pre-processing. I'm not going to spend a lot of time on this because I did in the previous video. I'm just going to pull up it here, and you can pause and read through it, or check out the previous video for more info. But basically, because we're not doing 2D game with 3D rigid bodies, and we don't have a weird problem with, as it explains, we don't want to use pre-processing. So we just want to disable that. And by default, we normally probably want to turn off pre-processing on most of our joints unless we are specifically experiencing the problems described. All right, and that's the end of the spring joint. So thank you for watching. Stay tuned for more videos. We're going to be covering all of the Unity joints for the 3D joints anyways. And if it helps you out, press like. That helps the channel. I thank you for that. And I'll see you guys in the next video.